Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 29, Types of Chemical Reactions, Part 4. Here are our objectives for today's video. So hopefully by this point in time, I have given you a set of solubility rules. It's just a PDF document that lists a bunch of stuff. For the purposes of the 10HH class, these are not going to need to be memorized. If you continue on to AP Chemistry, some but not all of them will need to be memorized. This is just a set of guidelines. They're not 100% rules set in stone, but they're pretty accurate, used to predict if an ionic substance will be soluble in room temperature water or not. Again, this list does not need to be memorized. I'll provide it to you just like I provided periodic tables and polyatomic ion sheets on all of your past assessments for which they have been useful, but you will need to be able to apply them. Pause here. Right, so all you really need for this is your set of solubility rules. So the first one I see AgNO3, so I go over to my list of solubility rules. I don't see, and by the way, you could ignore this bottom table. You don't need it for right now. I don't see Ag in any of these, so I'm just moving on to the next thing, NO3. I see that it says that it's always soluble with no exceptions, so AgNO3 is soluble. Now on to AgCl. So I don't again see Ag, so now I'm looking for Cl. So this third rule says that chlorine, bromine, iodine, all other halides, so that also includes fluorine, are mostly soluble, but silver is an exception. So instead of being soluble, it will be insoluble. So the exceptions just take whatever the general rule is and make it opposite. I don't know why that says a 2 there. That's just NaNO3. So there is a rule for Na. It's always soluble, no exceptions. I don't even need to check the rule for NO3, but if I did, I would see it's always soluble, no exceptions. If there happens to be two rules, they will not contradict one another. So you could just check one of the elements in the event that there are two rules. And then last one, calcium carbonate. I don't see calcium in here, and I'm always just checking the left column. Now I do see carbonate. It is mostly insoluble. I checked the exceptions. Calcium is not there. So this is going to be insoluble. Pause here. So the reason why we care about if something is soluble in water or not, besides some of the more obvious things, like if you want to clean something, it's way easier to do if it's soluble in water, is we want to be able to write precipitation reactions, also called double replacement reactions. We want to be able to predict if we mix two substances together, are they going to produce a solid that not? In chemistry and many sciences, precipitate actually refers to a solid. I know in some of your more earth science classes, you refer to it as liquids, but in chemistry, we refer to it as solids. Pause here. You don't necessarily need to follow these 4 steps exactly as they're written. I include them because a lot of students like to have just a set of steps to go through. But again, if you can sort of intuit your way through it, there's nothing wrong with that. Some students like to write pre-work where they write out all of the ions first. You're going to write the reactants, so you're just crisscrossing like we normally do. You swap partners, you're essentially crisscrossing again, ignoring what you did the first time. Balance the equation just because everything has to be balanced. And then we use the solubility rules to determine if a solid forms or not. Let's work through an example with this. Pause here. So some students like to just list all the ions at the top of their paper before they do the rest of the problem. So I'm actually going to go ahead and do that just in case that describes you. I have my 4 ions. Now for my first step, I'm going to get both of my reactants. So I just crisscross Ag and NO3, I get AgNO3. I crisscross Ca and Cl, I get CaCl2. I'm going to go back later and put in the state so you want to and balance. So you want to give yourself a little room around each compound. Now I'm going to swap partners. So Ag is now going to go with Cl. It's always going to be positives with negatives. So I get when I crisscross AgCl, and then I crisscross Ca2 plus with NO3 minus. I get CaNO3 2. Just keep in mind that the positive ion always goes before the negative ion when I'm writing the formula the for compounds that are ionic. So I re-crisscross what I get in the first half does not necessarily impact my second half. And then I have to go back and I balance it. To balance it, I end up putting a 2 here and a 2 here. Now for all four of these, I check if they're soluble in water or not. You could always assume that the reactants are soluble and you don't need to check it. For this one, NO3 is soluble with no exceptions. That's why that's soluble. Chlorine is soluble and calcium is not an exception. So that is AQ. AgCl, that is insoluble. We already did that example. So insoluble means solid. And then nitrate is always soluble with no exceptions. So it gets AQ. So if something is soluble, it takes on the state of aqueous. And if something is insoluble, it takes on the state of solid. Pause here. So if you have something that is aqueous on both sides of the equation, that means that it's not actually doing anything. It's just dissolved, dissociated on both sides. That's why it's called a spectator ion. It is just in the solution the entire time, not really doing anything. Pause here. So then we have net ionic equations, which is just the equation without the spectator ions. So I have an example of what we call a molecular equation. That just means the regular equation. And so if you take a look at this, Na is soluble on both sides, so I just remove it. NO3 is soluble on both sides, so I remove it. And all of a sudden, we get something that is just a dissociation reaction in reverse, and that is our net ionic equation. Pause here. Right, so we are just adding on to what we've already done. Another way you can think about it, you could start with a product, which is going to just be whatever is soluble, or sorry, not soluble, insoluble. And then the ions that form it on the left. Some of you are probably wondering, why did I ignore the 2 that was in front? You're going to rebalance it. Had I kept it there, it would have been fine. I would have gotten 2, 2, and 2, and then I would have needed to simplify the equation to 1, 1, and 1 for the balancing. And then for the spectator ions, you just list what they are. It's not like something that you need to balance. So the net ionic equation handles whatever is soluble in the product, and the spectator ion handles whatever is insoluble in the product. Right, that is all for today's video. Thank you so much for watching and have a great night.